Hello everyone, welcome to another exciting installment of Dave Does Math from Home. Today we're talking about section 5.1. We are leaving functions behind for a little while. We're going to talk about angles and radians. So this will probably be a few videos, so we'll call this part 1. If we're going to talk about angles and radians, the first thing we need to ask ourselves is, what is an angle? And this is a much more deceptively difficult question than we sort of expect it to be, because we all kind of inherently know what an angle is, but finding the correct words that will accurately describe what an angle is and what it measures are actually pretty difficult. And I think the best way to describe what angles are and what they measure is with the description: a measure of the same directionness of two lines. So, if we're going to have an angle, we need two lines. They need to be intersecting lines. I should probably write two intersecting lines, but I don't want this definition to get too cluttered. We'll just know that these lines are intersecting. So we have two intersecting lines, and we use angles to measure their same directionness. And this idea of same directionness is critical to the idea of angles, because the most important thing we need to talk about with respect to angles is how to distinguish between big angles and little angles. So, in regular classrooms, when I'm asking this question to a class full of students, I very commonly get answers about the distance between two lines, or the space between two lines. And those are great ways to start thinking about this. But the thing that we have to be really, really careful about if we're talking about distance or space or area is we need to describe the idea of an angle without any references to the size of these lines. This is a small angle drawn with really big lines. This is a big angle drawn with really small lines. Whatever words we use to describe what the angle is and what it means has to take into account the fact that this is a smaller angle than this, even though this has more distance, more length, more space, more area than this. And that's why we need this idea of same directionness. The same directionness of two lines has nothing to do with how long they are, or how big they are, or anything like that. It's just about what direction they're going in. So this one is going east, this one is going east by northeast. So these have a small angle because they're pointing in very similar directions. This is going east, this is going northwest. This is a large angle because these are pointing in very different directions. So that's the idea of angles. We need it to be independent of size, area, space, length, distance, all of that. It's just about directions. So let's talk more about angles. Angles are measured in degrees. A degree is 1/360th of a circle. So the idea of circles is very closely related to the idea of angles. If you sort of start with one of your directions being east and look at all of the possible other directions angles could point in, or lines could point in, you end up with this full circle sort of arc of possibilities. That's why circles get into this. I haven't mentioned circles before. We just find this using lines, so I want to make sure everyone knows that they are also connected to circles. Full circle has 360 degrees, which means 1 degree is 1/360th of a circle. And the reason for this, I very recently discovered, is because of ancient Babylonians and Assyrians. They did math in base 60. And one of the big reasons they did math in base 60 is because they didn't have calculators or cell phones, or they might not have even had abacuses. I don't know. I don't know when the abacus got invented, but I definitely do know that whatever they were doing 3 millennia ago, complex calculations were very difficult. You had to do them by hand, took a while. So using a number like 360 that is divisible by lots and lots and lots of things is a really good idea. You can divide this number by 2, 3, 4, 5, 6. All 5, the first 5 important numbers all divide very cleanly into this. You're missing 7, but that's fine. 7 doesn't show up often in situations. Kind of a weirdo. This is divisible by 8. It's divisible by 9. It's divisible by 10. So of the first 10 numbers, the only one you're missing is a really clean divisor is 7. You also miss 11, but you get 12. 12 is super important. You're missing 13, 14. You get 15 though. So of those first 15 numbers, you're only missing 7, 11, 13, 14. You're only missing 4 of them. You can divide this really nicely by a ton of different things. And that made it really, really important for mathematicians in kind of throughout history. Starting with the Assyrians and Babylonians, but moving straight through. Degrees got used a lot for navigation, especially nautical navigation. If you were some sort of 16th or 17th century seafaring sailor and you needed to know where you were going and figure out which direction to point your boat in based on the positions of stars, using degrees to figure out which direction to go in was extremely important, and being able to do that math by hand without getting crazy complex decimals involved was useful. So that's why 360 was used in the beginning and why it continued to be used throughout most of history. The problem with that is, at this point, in the year 2020, those of us doing this math with degrees in the pre-calculus class at this point are all adults who do have access to calculators and computers and cell phones. We can do this arithmetic very easily. We are not daunted by decimals or weird divisions, and so most of the utility of this number is sort of lost on us. It's kind of wasted. We don't need that. So most of this lesson is going to be spent introducing us to a separate way to measure angles. It's not degrees. It's called radians, and we'll describe what those are in a second. Before we get too into describing exactly what a radian is, I want to continue making the case for why they're important. The difference between degrees and radians, I think of it as very, very similar to the difference between the imperial system of measurement and the metric system of measurement. So if you think about meters and kilometers versus feet and miles, this perspective is from someone who's pretty American. I was born and raised in America. I've always used feet and miles and everything. Like, they're familiar to me. I know about what that is. So like if someone tells me that they're 5 feet 10 inches tall, I know how tall 5'10" is. If someone tells me that they're 1.73 meters tall, I have no idea what that means. Like, maybe that's tall, maybe that's short, maybe that's average. I don't know. I'm not familiar with meters. And that's kind of a problem for me, because I wish I was familiar with meters. Meters is, by every reasonable estimation, the much more useful, the much more easy to work with way to measure distances and lengths and heights. I wish it just came naturally to me, but it doesn't, because I was taught in this stupid nonsense feet, inches, miles, yards crap. Who even uses yards anymore? Football? Get over yourself, football. No one cares. So I wish we could use meters. Meters would make everything much, much, much easier. But feet and inches are what I'm familiar with. The same kind of relationship happens between degrees and radians. Degrees is sort of what everyone is familiar with. It's what you grew up with, it's what you know. If I say 90-degree angle, everyone knows exactly what that is. That's the right angle. If you say 60 degrees, that's acute but still kind of big. 45 is half of the 90. Everyone's really familiar with these degree measurements because that's what you've been using all your life. We're gonna switch to radians by the end of this, and hopefully by the time we get there, we'll be able to appreciate why radians are the better way to measure things. Kind of like meters and kilometers. Like, the transition into radians is going to be rough because you're unfamiliar with them. But once you make that transition, looking back, I hope that you will be able to recognize it was smart to transition. And the reason we're going to do this is because in most of the sciences, and especially in calculus, it's all radians all the time. No one ever really uses degrees at all for anything in calculus. And since we are going to be using sines, cosines, tangents a lot in calculus, it's important to recognize the radians and what they mean. So let's talk about what a radian is. A radian is defined as the ratio between the arc length and the radius of an angle. And it has to be this ratio because both of these things, if you think about an arc length, this is obviously a length, it's a distance. You would measure this in meters or feet or inches or whatever you like. Radius is also a distance. This thing gets measured in meters, feet, inches, whatever you like. And we said at the beginning of this video that it was very important that we, however we measure angles, we have to make sure that they are not dependent on how big we draw them. So we had the big lines that had a small angle between them, and we had the small lines with a big angle between them. And we talked about how it was important we keep those ideas separate. Whatever we use to measure angles, it can't depend on how long these lines are, or how much space is between them, or how much distance is between them. And our solution to that is really elegant. We're going to look at the ratio of how long the lines are to how much distance is between them. And that's going to take size out of the equation by looking at the quotient of those two things. So if we look at our small angle with a big lines thing we were looking at before, if you want to mark it here and look at the arc length between those things, this distance would be the arc length, and this whole distance from here to here would be the radius. And if you look at that ratio, you'll get an angle as measured in radians. And if you want to do something much, much smaller, like if you wanted to see what happens if you took this same basic angle and only made it half as big, your arc length would be half the size, and your radius would be half the size. And so all of these things would scale proportionally and give you the same ratio. That's why radians are a great tool for measuring the angles of things, because when you scale the arc length and the radius, those two things scale proportional to each other. And so when you take their ratio, that proportionality kind of disappears, it cancels itself out, and all you have left is a measure of the angle, the same directionness, which is what we want. So we can run through one quick example of that, see what that looks like. In class, I used 60 degrees, so I think this time I'll use 45 degrees. And I'll put the 45-degree angle on a coordinate grid because I can. Actually, we're at the 15-minute mark, so let me cut this here, and then I'll start the next one with this radians example.